Hello, we'll be looking at the solutions for dual nature questions, which has appeared in your CET Test 5 paper. Very conceptual questions. None of them require so much of time working out with substitution of formula and stuff. So let's see the best approaches for each of the question. Let's straight away jump into the first question. In photoelectric effects, the velocity of the ejected electrons depends on, very well, the velocity of the electrons would determine its kinetic energy, right? Because kinetic energy formula is half mv square. So indirectly, they're asking the kinetic energy of electrons depends on what? The kinetic energy of the electrons, if you look at the Einstein's photoelectric equation, kinetic energy of electrons is energy incident, right, minus threshold function. So energy incident depends on frequency of incident light, and threshold depends on the nature of the metal. It might be potassium, sodium, lithium, whatever metals they are. So the kinetic energy depends on the frequency of the incident light, and threshold depends on the nature. So it depends both on the nature of the target and the frequency of the incident radiation. Most appropriate choice. Minimum use of equation, maximum concept. Same can be said about question number two. What does a photoelectric current depend upon? The very funda of dual nature tells us that current depends only on intensity, whereas the kinetic energy or stopping potential depends on frequency. The dual nature rests on these two concepts in graphical form and equation form, right? So current is proportional to intensity, and that would be option A. Now, question number three, how does energy of a photon vary with the frequency of the radiation? This is directly from the Einstein's assumption that energy is in the form of pushes called photon. Energy is equal h nu, which means energy is directly proportional to frequency. This is in the form of Y equal to mx. How? Energy is plotted in the y-axis, frequency in the x-axis, h is a constant, so y equal to mx. Y equal to mx is nothing but a straight line passing through the origin. So the third one goes with the fourth option. Third question, fourth option. The fourth question, Planck's constant has the same dimensions as. Well, here they have linked the dual nature chapter to units, measurements, and dimensions, which every NCERT textbook has at the conclusion of the chapter. There's a table given, each quantity with its unit and dimensions. So let's explore Planck's constant, E equal to h nu. So h should be equal to E by nu. E, right, is ml2 t minus 2. If you remember, energy is force into distance. Force is mlt minus 2, distance is L, so ml2 t minus 2. Nu is 1 by t. And here we have ml2 and t minus 1. What is ml2 t minus 1? This one is, if you look at it, ml2, mr square, it is a moment of inertia, and t minus 1, the t minus 1 must be 1 by t. 1 by t can be thought as angular velocity, omega. So ml2 is I, t minus 1 is omega. So it has the same dimensions as I omega. Which physical quantity has a dimension of I omega? First, uh, a pre-cap or a recap of 11th portions. I omega is nothing but angular momentum L. So it is angular momentum. Planck's constant has the same dimension as angular momentum. If you do not recall angular momentum, I mean, what is this? Well, there is one more shortcut. If you don't go by, this is a conventional way. What is the other way? The other way is not based on dual nature, but it is based on atoms, right? In atoms, Bohr told a very wonderful thing, that angular momentum is an integral multiple of h by 2 pi. So the dimension of h should be the same as the dimension of angular momentum. This is a quick approach. But in the textbooks, you don't see this. You see often equal to h nu. What you can do is you can use both quantization rule, L is equal to NH by 2 pi. N by 2 pi is simply a number. A number has a dimension of 1. So L should have the same dimension as H, or in other words, the dimension of H is the same as L, which is angular momentum. That is the fourth question. Question number 5. The energy of a radiation photon corresponding to the maximum wavelength of visible light is. So here is where you need to, this is a memory based question, all right. Even if you don't do this, well, you are excused because it's memory based. Maximum wavelength. So what you do is you say that energy equal to hc by lambda. But look, everywhere there is EVs, energy is in EVs. So we don't use hc by lambda form. We have discussed a shortcut in the class. What we do is energy in EVs is 12,400 by lambda in angstroms. This will directly give you energy in EVs. Now put to lambda. What is the highest wavelength of visible light? You put that number over here and you get corresponding energy in EVs, right? As simple as that. We don't need to calculate or substitute H and C. You simply put lambda value. You can search it up. You have the NCRT with you. So visible light window ranges from 410 to 720. There's a window. So what is the maximum wavelength? You put that number over there. You'll get the corresponding energy in EV. Well, now the sixth question. The photoelectric threshold for a certain metal surface is 360 angstrom. If the metal surface is irradiated by a wavelength of so and so, what is the kinetic energy? A very nice question. So what you do is, we know that photoelectric emission happens if and only if lambda of incident light, it should be less than lambda of threshold. Why? Because there is a relation between energy and wavelength. Energy is always inversely proportional to wavelength. Smaller the wavelength, greater the energy. Compare the two wavelengths here. Threshold wavelength is lesser, therefore threshold energy is greater than whatever energy is I am shining upon the metal. Therefore, no electron is emitted. See, this condition is not satisfied for the above question. So no electron emitted. If there are no electrons emitted, what should be the kinetic energy of the electrons? It should be 0. We are not calculating again. We are not putting in we are not plugging the values in Einstein's equation. All we are doing is saying is, look, incident energy is lesser than the threshold energy. So electrons can't escape from the metal surface. Therefore, the kinetic energy is 0. That would be question number 6. Now, question number 7. Metal surface is illuminated by light of intensity I and electrons the maximum kinetic energy Ek. Now the intensity is reduced. Remember, only intensity of the light is reduced, frequency is still kept the same. And then they're asking what will happen to maximum kinetic energy. Quick recap of this video only. You have a look at this. Kinetic energy and stopping potential depends only on the frequency. In this question, only intensity is being changed. Frequency is kept a constant. So kinetic energy of the electrons will not change. Therefore, it will still be the same. See, we are not working out much. We are simply saying, since the kinetic energy depends only on the frequency, frequency is being held constant. It is independent of intensity. Therefore, the kinetic energy shall remain the same. Next, there is a light of wavelength lambda, momentum P, and E. What would happen if the wavelength of the radiation is increased? Well, um, we have the following relation for light. E equal to hc by lambda and lambda equal to h by p. This holds good for light. Both the equations hold good for light. Now, if wavelength is increased, then definitely remember energy and wavelength are inversely proportional. Energy should decrease. Which of the options says energy will decrease? Only A and C, right? Now, if a wavelength is increased, that would mean momentum has decreased because lambda and p are inversely dependent. So momentum should decrease and energy should decrease. Where is that? That is happening only in the case of A, hence I go with A. Stepwise elimination. I simply see first way which of the options shows a decrease in energy, only A and C shows. So between A and C, how to choose? Look at momentum relationship. If lambda increases, momentum should decrease. So that is question number 8. Question number 9, a very highly conceptual question in the entire paper. What is happening is there is an emitter. Let us say this is the emitter plate, and I am shining light on it. Electrons are being ejected. Now, within the tube, an electric field is produced which has a vertically downward direction. So there is an electric field which is, this is emitter, okay? Now, there's an electric field which is pointing downwards. What would happen to these quantities once I switch on this electric field, right? So, let's see this. Will something happen to photoelectric current? No, because photoelectric current depends only on the intensity of light which I'm shining. So A option is false. What will happen to stopping potential? Or what will happen to kinetic energy? Let's have a look at kinetic energy. You see, if I switch on an electric field in a vertically downward direction, from our electrostatics knowledge, we know that electrons experiences a force opposite to that of electric field. So every electron will be pushed up. It will speed up, right? So what will happen to the kinetic energy of electrons? The kinetic energy of the electrons increases. If kinetic energy increases, we know kinetic energy and stopping potential both are directly proportional to each other. So we know the relation Ke equal to EVS, right? If Ke increases, EVS should also increase. The only possible option is option B, where it says kinetic energy of electrons will increase. Reason, electrons always feel a force opposite direction of electric field. They will speed upwards, so its kinetic energy is increasing. What would have happened if if an electric field upward would have been there? Well, electron would feel a push downward. So they are being emitted in the upward direction, but they would feel a pull downward, then their kinetic energy would decrease. Then it would have made sense. The third option would have made sense if electric field were in the upward direction. Now it is in the downward direction. So electrons would speed up and hence its kinetic energy is going to increase. That is question number 9. Question number 10, it is strictly not in the scope of dual nature. Reason, it is in, excited hydrogen atom. It's not in the scope of dual nature, but still you should know how to do the question. Well, the ratio of recoil energy to photon energy. What is happening is there is an atom. The atom has now emitted light. As a result, the atom recoils backwards with some kinetic energy. What are they asking is what is the ratio of this kinetic energy of, like imagine a gun firing a bullet. A bullet moves forward, but the gun recoils backwards. What is the ratio of this kinetic energy to the energy of the light? Right? So that is simple. How is it? Because momentum is conserved. If I say that the light is going forward with a momentum of p, the atom would go back with the same momentum. Reason, initially the atom was at rest. So to conserve momentum, if the light carries a forward momentum of p, this would go backward with a momentum of p. How does it help? Well, we know that for light, E equal to PC. Energy of light equal to momentum of light into speed of light. So what is momentum of light? Momentum of light is nothing but energy by speed of light. Okay, that's all I need. Now I take the ratio of the Ke to E. Kinetic energy of the atom can be expressed as P square by 2m, where P is its momentum and its momentum is the same as light's momentum. And what is energy? Energy would be simply E. Energy of light is simply E. What is P? P is nothing but E by C. P is E by C. So you now know everything in this ratio, because what is the energy released? Energy is released from n equal to 3 to n equal to 2. That is from the famous formula, energy equal to 13.6 times 1 by 4 minus 1 by 9. You must remember this, 1 by n1 square minus 1 by n2 square, where n1 is less than n2. This is energy of the light released. I know that. I can put it over here. Mass of the atom, hydrogen atom is nothing, but it weighs as much as a proton does. So you know the mass of hydrogen atom. And then C being the speed of light. Okay, so we know all these values, we plug it in and we get the answer. So this is how you do the 10th question. What are the key concepts here? The key concept is relating momentum of light to its energy. We know energy easily by the Bohr's energy formula. We don't know its momentum. So we express momentum in terms of energy, and we apply momentum conservation to the atom. If it shoots a photon forward with energy P, the momentum itself will get a backward momentum, will get a backward push, and its momentum will have the same magnitude as the light's momentum. Momentum is a vector quantity. Forward and backward momentums cancel each other out, because we know initial momentum is zero because atom was at rest. Finally, also the momentum should add up to zero. Multiple concepts involved here: energy, momentum. The question can't get more wonderful. That is question number 10, but it has less correspondence to dual nature, more of an atom question. Question number 11, right? First of all, the surface thickness has zero role to play. Don't look at this. It is irrelevant information. Now, with light of wavelength lambda, stopping potential is V naught. If wavelength is increased, stopping potential becomes V naught by 6. What is the threshold wavelength for the metallic surface? This is a play of equations. Though you can, if you're smart, you can eliminate the options and come to it, right? Uh, okay, you can arrive at it, but you you have a higher chance to get the answer once you put it in numbers. How is it? Well, question number 11 के लिए, what we do is we say hc by lambda incident energy is equal to the threshold energy plus EVS. We choose this form of an equation, right? The initial wavelength is lambda, stopping potential is V naught. Now it became 3 lambda, stopping potential became V naught by 6. So, and they're asking for phi. Phi I can write as hc by lambda naught. Various avatars of photoelectric equation, this is one of them. So, hc by lambda equal to hc by lambda naught plus EV. Now, hc by 3 lambda. Wavelength has now become 3 lambda. Then this will be still remaining the same. V becomes V by 6, EV by 6. Two equations out of which I don't need EV. I don't need EV. So what I do is I will multiply the second equation with 6 everywhere, so that EV by 6 into 6 will just become EV. Then subtract the two equations and get lambda naught in terms of lambda. Right. First, the Einstein, you need to choose appropriate form of photoelectric equation, Hc by lambda equal to Hc by lambda naught plus EVS. Then put for lambda as V and 3 lambda as V by 6, and then you have it. You eliminate EV. We don't need V in the setting. So eliminate EV by multiplying the second equation with 6, subtracting the two equations, and you get lambda naught in terms of lambda. That would be question number 11. Now, question number 12. A red bulb and a violet bulb of equal powers emit NR and NV number of photons in a given time. Then, what can I say about the setting? Well, here you need to know the formula of uh, P, P equal to NH nu. P equal to NH nu. P is power of light. N is the number of photons emitted per second, which is given, and nu is a frequency. We know both red and violet have the same power. So NR nu R should be equal to NV nu V. Why? Because both of them have the same power. Both red and violet have the same power. So NR nu R should be equal to NV nu V. So frequency frequency of red is less than frequency of violet. Only if you know this, you can do the question. Frequency of red is less than frequency of violet, right? So if I say that n nu is constant because nr nu r equal to nv nu v, n nu is constant. If nu becomes less, n has to become more. So if frequency of red goes down, to keep the ratio the same, the number of photons per unit time n has to go up. So frequency of the number of red photons has to be greater than number of the violet photons. So the appropriate option is B. If you don't like this approach, what you can go conventionally is NR by NV should be equal to nu V by nu R. Frequency of violet is greater than frequency of red. So this whole thing is greater than 1. So I can say NR is greater than NV. We straight away arrive at this. But if you are a logical person, you can say that if frequency is less, to keep the ratio, to keep the product the same, n should go higher. That is the appropriate way to look at question number 12. If you don't know the power relations, you're gone. We can't do much here. So P is equal to NH nu, where N is number of photons emitted per second. Now, question number 13. In question 13, there is the source is at zero point 0.2 meters, and stopping potential is 1 volt and saturation current is 27. If the same source is placed at distance of zero point 0.6, what will happen? All right. Uh, we know that the only thing that has to do with the source and the target, between them there would be some distance. What is that quantity which will change if I change the distance between source and the target? The only thing that will change is intensity I, right? Intensity of light is going to change if I change the distance between source and target. If I make the source come closer, intensity increases. If I take the source away from the target, intensity decreases. So what is happening here? Intensity of light is decreasing because initial distance is 0.2, final distance is 0.6. So I am taking source away from the target. So the intensity is decreasing. What is the quantity which is dependent on intensity? Of course, current. So current should reduce. Okay, current should reduce. What will happen to stopping potential? It will not change. Reason, we'll go back to that two lines written, the golden lines. Stopping potential depends only on the frequency of the light. It doesn't depend on intensity. So stopping potential doesn't depend on the intensity. Only intensity changes if you change the distance. So stopping potential will remain the same. So I can eliminate option A and D. It should be either 3 milli or 9 milli. How to get to the root of this? Well, the relation is stop the current, okay? Current I is proportional to 1 by d square, where d is the distance between source and target. What is the relation between zero point 0.2 and zero point 0.3? If you divide the numbers, you see that the 0.6 by zero point 0.2 is 3. So I am actually increasing d by 3 times. So what should happen to current? D square, right? Current should reduce by 1 by 3 square 9 times. Current should reduce by 9 times. So if it was 27 milliampere, 27 by 9, the final current should be 3 milliamperes. Reason? Distance increased by 3 times, so intensity should reduce by 9 times, because intensity is inversely proportional to square of the distance, but intensity and current are directly proportional to each other. Intensity and current are directly proportional to each other, so I can say current is inversely proportional to square of distance. If distance increases by 3 times, then current should reduce by 9 times. So the answer is B. 13-1 goes with B. Next one, a standard textbook question, I versus V graph, and we all know it should be option D, where this is the stopping potential and saturation current and stuff like that. So 14th one goes with D. Standard question. 15th one, stopping potential versus frequency is given. I need to compare work function of metal A and metal B. How to go for it without using much formulas? What we can have, or what we can conclude about this is, you see, uh, photoelectric emission begins for metal A at a higher frequency than for metal B. I can say the frequency of radiation required to start photoelectric emission is greater for metal A than metal B. What does that mean? That means threshold energy of A should be greater than threshold energy of B. Because I need to increase the frequency for photoelectric emission. We know that frequency is directly proportional to the threshold, right? I need to supply metal A with more energy than metal B. Therefore, threshold of metal A should be more than metal B. So I can say work function of A is greater than that of B. That is the appropriate option. Why? Because this is nothing but the threshold frequency, the frequency required to just start the photoelectric emission. Threshold frequency of A is greater than threshold frequency of B. Therefore, threshold of A is greater than threshold of B. That is 15th question goes with B. Now, the 16th one. For the 16th one, they have given nu2 is greater than nu1. I don't care for the condition. What I do is I will suppose nu2 to be almost equal to nu1. If a nu2 is almost equal to nu1, then the new stopping potential will be the same as the old stopping potential. So if I substitute nu2 equal to nu1 in the options, I should be getting v1 back. So definitely option A is eliminated. It can be either B, C, or D. Now, how to make sense of B, C, or D? Okay. Well, if nu2 is greater than nu1, stopping potential is directly proportional. Stopping potential there is directly proportional to the frequency. If frequency increases, stopping potential should increase, which means the new stopping potential V2 is greater than V1. Which of these options makes sense in that way? This does not, because nu1 minus nu2 will be a negative number, and that way, yeah, and the resultant expression is becomes lesser than V1. So option B can't be. What about option D? This is negative, but negative into negative is positive. Here also, this entire thing is positive. So it might be C and D. How to choose between C and D? Here is where we pull up the card. The card is, I will put nu2 as 0. If I put nu2 as 0, which means I'm not shining any light at all. I'm not shining any light. If nu2 is 0, then emission is not happening. So V2 should be 0. If nu2 is 0, V2 should be 0. So if I put nu2 as 0 in between C and D, where will I get 0 as the option? Only in C, I will get 0 as the option. Why? You put nu2 as 0 there, we get V1 minus H nu1 by E. Okay. H nu1 by E is nothing but, V1. H nu 1 by E is nothing but V1. V1 minus V1 is getting cancelled. So the only option where you get 0 as key when you put nu 2 as 0 is C. So 16th one goes with C. 17th question. Photoelectric threshold frequency of a metal is nu when light of 4 nu is incident. What will happen to maximum kinetic energy? Okay. So simple application of photoelectric equation. H nu equal to phi. Phi can be written as again uh, H nu naught plus half mv square. This is the equation which I'm going to take the help of. I will put 4 nu as the frequency. 4 h nu. Phi can be written as h times threshold frequency in nu, h nu naught, and half mv square. I need that itself. So what would be Ke in terms of h nu? Kinetic energy will be 3 h nu. Take this h nu to the left hand side. 4 h nu minus h nu becomes 3 h nu. The 17th one goes with P. Right? The trick here is the frequency of incident radiation is 4 times nu, putting that. And threshold energy is h nu naught, where nu naught is given as threshold frequency. So 4 h nu equal to h nu plus Ke. Ke becomes 3h. Hmm. So, well, that is about 17th question. The 18th question. Ratio of the de Broglie wavelength of a proton and alpha particle having the same kinetic energy. We will use the appropriate form. Which form of de Broglie wavelength can be expressed in terms of kinetic energy? Lambda equal to h by square root of 2m times kinetic energy. So I can say that for the same kinetic energy, lambda is inversely proportional to square root of m. When I divide lambda of proton by lambda of alpha particle should be equal to square root of mass of alpha particle by mass of proton. This is a relation. Okay, this is a relation. Well, so if mass is less, lambda is more. Now, which of the options says this? If mass is less, lambda is more. So I can say that lambda of proton is greater than lambda of alpha particle. So when I divide both of them, I should get something greater than 1. So I can eliminate B and D because B and D suggests that the Broglie wavelength of alpha particle is more than the Broglie wavelength of a proton. That can't be true. Either it is A or C. But we again know that it is proportional to root of this. What is mass of alpha particle? Mass of alpha particle is 4 times mass of a proton. The reason alpha particle is nothing but 2 protons and 2 neutrons, and neutron and proton almost weigh the same. So I can say that alpha particle is made of actually 4 protons or 4 times weight of a proton. So mass of alpha particle is 4 times mass of a proton. Root of 4 is 2, and therefore A makes more sense than C. Right? So here you can adopt elimination as well as logic. Lambda proportional to root, and we know that mass of alpha particle is 4 times this. So 4 ka root is 2. The option should have 2, and lambda of proton should be greater than lambda of the alpha particle because mass of proton is less. The only thing that fits between these two conditions is option A. So hence we go with option. So 18th one goes with A. So these are the questions. Many of them needn't be looked upon as formula based if you just appreciate the physics that which is happening, especially the 15th question, how to compare work functions between the two. Well, metal A has a higher threshold frequency than metal B, therefore threshold energy must be greater. We didn't look at straight lines or its graph, slope, etc. Okay, so this was the discussion on dual nature in this paper. Hope this gave you some new insights and gave you some nice techniques and ways to think about the problems. Take care, and we'll meet with the JEE NEET discussion soon. So all the very best. Keep having fun with physics and keep doing physics. Take care. Bye bye.